Screen sharing. It's
Picture also rendered in the
it's good. It's dedication.
So, एक बार वो browser watch it again.
The pleasure to have Aalok Gangopadhyay from IIT Gandhinagar with us today. He's going to tell us about differentiable algorithms for representation, processing, and rendering of shapes.
Good evening, everyone. I'm glad to be here to talk about some of the works I've done as part of my PhD thesis. So it's regarding shapes and in the digital world, when you're storing shapes on the computer, how we process it and render it or even represent it. So I'm going to talk about differentiable methods to do that. So first of all, why do we care about shapes? So we have objects in front of us, the chair or the tables, and light is falling on it and it's bouncing and reaching our eyes, and we have an internal understanding in our brain about those shapes. And if you would like computers to give that representation or understanding of shapes, so that even they could interact with us if they have the understanding of shapes, and the understanding of shape is very crucial for our survival on a daily basis. So that's why we are interested in shapes. So first I'll introduce to the field of visual computing. So let's say we have a shape in front of us, like some cube, and we take an acquisition device to scan it. And that's when a shape is born in the digital world. Or we might use some modeling software to create shape using interactive methods. Once we have a shape, we might want to process it, edit it, or modify it to get another shape. Or we might want to extract information from the shape to understand something about it. Given information, we might want to synthesize shape. Now, given this shape, we might want to render it. For example, this slide, whatever is happening when I'm clicking a button, graphically some rendering is going on. So you might want to render it so that it's interpretable to a human visually. Or you might even want to manufacture it in the real world so that you could 3D print it and hold it as an object. And it's has application in various different domains.
So the last one was top place, something like a 3D printing there.
So the last part, manufacturing.
Yes.
So you might want to create it in the real, like you have a model in a computer, shape stored on a computer, and you want to generate it in the real world. So 3D printing is one example. So there are two important aspects of visual computing. One is how do we represent these shapes efficiently? And the next is how do we do processing, analysis, synthesis, or rendering of these shapes efficiently? How do we design efficient algorithms for this?
Sorry, stupid question. So I don't know if it's me, but those cubes look the same to me.
Those
What happened to the process then?
No, the cube is a symbol for shape. Like there is a shape, and it's more of a logo that it's a shape. And you have a shape, and the output is also a shape. So input is the shape, output is the shape. So processing means it takes the shape as input, does some processing, and gives the shape as output. So this is not a demo of some actual processing going on.
Okay.
So I'll come to that later. And today we are concerned about differentiable algorithms. So an algorithm would take some input and give some output. So differentiable algorithm means that we can compute the gradient of the outputs with respect to the input, so that we could use gradient-based optimization techniques, and even there would be some parameters in the algorithm, and the output might be differentiable with some of the parameters of the algorithm. So by differentiable algorithm, we mean the output is differentiable with respect to input and the desired parameters. And so today I'll talk about differentiable algorithms for these three aspects: for representation, processing, and rendering of shapes. So let's skip this one. So I talk about the there will be two parts. In the first part, I would talk about representation and rendering of shapes, and in the next part, I'll talk about processing of shapes. So here I'll start with the first topic, which is inverse perceptual art. So the application here is art based, where we design some problem, and it would involve representation and rendering. So if we look at these two examples, here there is a 3D model in the scene, and light is shown from somewhere, and it casts a shadow on the wall to create this meaningful image. Although this shape is not meaningful, the shadow casted is meaningful. And similarly, here we have this 3D real object, and this entire thing is a shadow. So this is called shadow art, where you're using light, which shone upon some object, create something meaningful. And similarly, instead of placing the light source, if there's a human in the scene, if that person looks from that location, even that person would look something, it would see something meaningful. So there have been previous work on shadow art, where they have used volumetric method, where these objects are represented as grid of points. And there's another work which uses differentiable renderer. These methods have used representation where the object is stored as volumetric grid, which is like a 3D grid of points, where a point is either present or not. Or it has mesh-based representation, where the 3D object, the surface of the 3D object is stored as a graph. In our work, we have focused, we were inspired by these shadow arts by Larry Kagan, where he uses these thin wire structures to create meaningful shadow art. So to formulate this, I mentioned some notations. So K denotes a knot, so which is an embedding of a circle in R3. And by H, we will denote homeomorphism, so which is a continuous function with continuous inverse. And we will represent H phi as a family of homeomorphisms. So H here is a single homeomorphism. H phi is, so phi is the parameter space, and given one parameter, it would give you one homeomorphism. So by deforming the template knot, we could get a family of different knots. So while knots homomorphic to it. Now, in order to create the wire structure type objects, we need a tube-like structure. So given a knot, we would take a point on it and take a sphere of radius r, and we would trace the sphere along this entire curve to get a tube. So this is a tube which is union of all the r radius balls along the curve.
So I ask you something. So is the knot is allowed to have a overlap or
No, it's not. It's circle. So the topology should be that of a circle. So connected. It has only. It doesn't have self-intersection, because otherwise it won't have the topology of a circle. So we have the tube, and now let's say we have this point here, which is a camera. So this is the location where the camera sits and the orientation, and this is the viewing region of the camera. So given a camera, it has these several parameters, where t is the location and theta is the orientation, how its axes are aligned. And f gives information about this red image plane, which I will mention. So D is the image plane. And D is at location z equal to fz, and its extent is fx, and its extent in y is fy. And this region in the wireframe is f, which is a viewing frustum. It means whatever is inside the region this frustum F is captured by the camera. Anything away from that or and the before that is not captured by the camera. So Z minus and Z plus. This plane is Z equal to Z minus, and this is Z equal to Z plus plane. And these planes are given by Fx, Fy, and Fz. So now we have the camera, the frustum, and the image plane. So we'll mention about the image grid. So this square is divided into W cross H grid. So there are W and H size of grid. And these are the location of the pixel points on the image. So rendering here, we define rendering function R as it takes a parameter phi, which defines a knot. It takes a non-negative real number, a positive real number, which is the radius of the knot. And C star is the space of all cameras. So it takes a camera configuration and a knot with the radius, and it gives an image I. So given a tube and the camera, it should create an image which is, if I look from this location of the camera, how would this tube appear to me? That is the rendering function. So the image generated we would denote as I hat. It is a rendering function for a given knot, radius, and camera. So this is how the image looks if we look at from the camera. Now, if we want to make some structure in real world, if we want to make it practically applicable, we might have additional constraint. For example, this entire knot should be inside a fixed region in space. So we might give some box and say that this object should be inside the box, or that there should be no self-intersection in the tube, or given which material we want to use for making the knot, there might be some bending limit on the knot, how much it can bend. And we might also want to minimize on the material cost. So the how much material is needed would be proportional to the length of the knot. So we might have these constraints. So we formalize this problem as follows, where given a target image I, we want to find a knot phi. So we want to find a knot phi, which when rendered, it gives an image similar to the target image. And there should be no self-intersection in the tube, and even a bending limit and the length limit, the maximum bending should not be violated, and the length should be within the maximum length. And phi naught is the constraint region, so the entire tube must be contained within that region. So this is the bending constraint, the length constraint, region constraint, and this is no self-intersection in tube. And we want the rendered image to be similar to the target image. And we want to find the embedding of the knot. That's the problem. So this is the proposed approach. This is the parametric family of homeomorphisms here, and we've taken a template here, template shape. So
you're fixing what you want to see, and you want to find a knot that
yes
results in that. Okay.
It's the embedding of the knot is the unknown which we want to search.
Okay.
And the target image is given. The radius in this framework it is fixed. Radius is also given by the user, but we can even keep this here as a parameter. So
radius is the wire.
yes, like if the user is already knows that I want this radius wire, so find the embedding for this radius tube. But if he has freedom for the radius, so that can also be optimized. So here this is a family of homeomorphisms, and we have a template shape. So for example, a template circle, and by changing this homeomorphism, the tube shape changes in space, and we look from the camera, we render these images. So we might want to minimize these self-intersections in knot. And if in this region, this area is going outside some constraint region, then so here we take the constraint region as the frustum itself to illustrate that this region is of the tube is going outside. So you might want to penalize these, or if there is some severe bending, you might want to penalize them. So the first, we propose loss functions for this. So the first one is image loss, where we the rendered image is compared with the target image, and the L2 norm is the error. The second is length loss, where if the length is exceeded, then we add penalty to it. So if this length is greater than the maximum limit, then it is penalized. It's considered as loss. And for the self intersection, along the knot, if we look at some nearby region, for example, the white and the pink. So for this, the Euclidean distance and the geodesic distance, the distance along the circle, those would be same. So these two terms would be same. So this is the Euclidean loss and this is the geodesic distance. So for nearby points, these two values would be same. So there would be no penalization for this because these are not self-intersection. But if we take yellow and white, so these are far away, but in the embedding, those are nearby. So the yellow and white, those cases would be penalized. And similarly, if any part of the knot goes outside the region, then that would be penalized if that exceeds the region. Similarly for bending loss. So we define these loss functions. And for representation of homeomorphism, we use the idea from in real MUP, there's an idea of affine coupling where you want to design an invertible function. So the idea is if we get some input, so in this case we have 3 coordinates x, y, z. It works in general for arbitrary number of components. So we divide into 2 parts, the upper partition and the lower partition. So the upper coordinates are passed through identity. So as it is, they are sent as output. And the lower one is modified. Based on the upper values, those are passed through a function to predict a scaling factor and a translation factor. So this scaling factor, it's made sure that it is greater than 0. And this could be anything, negative as well. So then it is scaled and then translated to get the output. And from the output, we can exactly recover the input because the other 2 components are identity as it is, and the affine function for scaling factor greater than 0 is invertible. So it is, let's say this is S and this is P and this is Z. So we get S into Z plus P. Then here we subtract the P and divide by S to get the 3rd component.
Hello, hey. Sorry, could you explain what NDP stands for?
Non-volume preserving. So one is volume preserving transformations, and in another, the volume need not be preserved.
Okay, so in this forward pass, we do have bunch of ReLU layers, right? But ReLU is not in vertical. So we have a bunch of ReLU layers in forward pass, right? But ReLU is not in vertical. So how do you get around that?
ReLU is not differentiable, and
but it's not in vertical also.
It is continuous and for zeros.
So a lot of outputs map to 0 with a ReLU function.
Yeah. So this function need not be invertible. This structure is invertible. This can be any function. This part need not be invertible. Because this is used in the forward pass in both the cases. It could be anything. This function could be any differentiable algorithm.
So what is invertible?
It is something.
So this construction, let's say you learn a function here and you learn another function here. Given x, y, z, the z value is modified according to these 2 functions. And then if once the XYZ is modified, you can recover the original one. So there are stacks of this. So this is one green layer,
With special,
and there are many green layers.
like one specialty of this, there is any function X, and you map here xy to x comma x plus xy.
Oh.
That is inverted.
Oh, I see, okay, that's.
This is inverted.
So that's so then this could be anything, and this could be learned, and many such components could be stacked together to learn complicated functions. And we design the differentiable renderers for this. So in the tube, we assume that there are, if we take finite number of points on the knot, then we can approximate it as the sequence of capsules. So this is a capsule which has a cylinder with spherical ends. So if we take two consecutive points on the knot, then we can consider it as a capsule. So in the ellipse renderer, we take a knot and we sample many points from that knot and just compute the projection of the sphere on the image plane, which would be an ellipse. So in the ellipse renderer, finite number of points are sampled and the ellipses are computed. And in the capsule, these shapes, many such shapes projections are computed. So here for the capsule, this is the first ellipse and this is the second ellipse. And this is a quadrilateral. So the entire shape can be taken as union of these three components.
That takes in the not looking towards piecewise linear.
Yes, so piecewise linear approximation of the knot. Because in this model, we can just find deformations of the knot from the circle. We have the initial circle here, which has a algebraic equation. We can embed a circle in any way and sample points from the circle and find the deformed location of those points. But we don't directly know the entire shape of the curve itself.
And that is given by the element.
Yes. So this deformation, when we pass points in the circle, these region we get the output not points.
Hi, sorry, on the previous slide, so could you explain how the bending loss is calculated?
So that is done using so it's a discrete approximation of turning angle. So we take a point here and we take adjacent points and we compute how much turn it's turning. So here the SUP is, so we are on the image plane here. Let's say we have found the equation of this capsule projection, and we have the sign distance function which says for any point on the image plane, how much far away it is from the boundary and whether it's inside or outside. Sign distance. So the sign says inside or outside, and the distance is distance from the boundary. So once we have the sign distance, we can use some sigmoid function or any function which maps from 0 to 1. So if it is positive, it's inside, then this value would become 1. And if it is negative, but that is it's outside the shape, it would map close to 0. So from that we get a occupancy value for any query point on the image plane. We can compute a soft estimate of whether it's inside or outside. So it's not hard, it's a soft estimate and it's differentiable. So then this is the image given a query point. We find all the capsules that are being sampled, and from all the capsules we found which is the nearest capsule. So there might be multiple capsules projection in the image plane. For a given query, we find the nearest capsule, and if the nearest capsule says that it is outside, then it is definitely outside. Because if the best case is saying that it's outside, then it's outside. And if the best case says it's inside, then it's inside. So the best case value is used here to compute the pixel color.
It's not differentiable.
It is differentiable in the sense when we are implementing max, the max value location is stored. Then it just becomes, let's say we have X ABC, max of ABC.
But
Yeah.
process
So their tiebreaker is use whichever is chosen at the time that information is stored, so it becomes differential. And so that's how we get the pixel value at each query. I quickly go through this part. P is the point of the node on which we have a radius r sphere, and we have a cone. So XYZ is a arbitrary point on the image. So this sphere on the origin, we will connect this point to the origin, and this radius r, it would subtend a cone, and that cone, arbitrary point on the cone, is given by XYZ. And we use these two relations, that is this dot product between this vector line on this XYZ and this point, this cos theta, the aperture of the cone. That gives one relation. And the other is in this triangle, this is R and this is LMN vector. So we get the cos theta from that as well. And equating the two, we get the equation of the cone. And we have the image plane z equal to fz. So if we take the intersection of the plane with the cone, we get the equation of the ellipse, which is in this form. So the input point is LMN, and these are all differentiable functions with respect to LMN. And so we plug in a query point xy in this equation, then positive and negative, it would give the sign distance with the normalization. So this is how we have the differentiable render for the ellipse.
Hello, hi. Sorry, just a quick question. So in the ellipse renderer, what is the ellipse? I just completely understood.
So here in this, so this node, if we take a point on the node and we get the tube by taking a radius r sphere,
Right.
so we are taking finite number of samples from the nodes. We get finite number of spheres. Each sphere will have a ellipse as projection on the image plane when viewed from the camera location.
Okay, and why is that ellipse useful?
Because you want the image to be close to the target image. That was the original objective. Like if I look at this wire, which is having some radius, if I look from one angle, it looks as something, from a different angle, it looks as something else. So how do I bend this wire so that it resembles some?
No, that's a problem. I know that. But like, where did this show up in the equation? Ultimately, we had an optimization problem, right?
Yes.
That problem, where does this path go?
This is the image loss. I hat. This is I hat, and I hat is this rendering. This is the ellipse render or the capsule renderer.
Oh,
This is the rendering function.
We also have control over the relative position of the camera and the screen.
The camera and the screen. So those are given as camera parameters here. So these values, the location. So here it's assumed that the camera is fixed.
Okay.
Because I'm in a space.
But the screen?
So screen is taken at an arbitrary exact value and it's normalized. So it's divided. This normalization is
The
happening.
reason I'm asking is that if you're only allowed all, then you will never get an ellipse unless you're allowed to have the camera angle hit the screen at a certain angle, right? Otherwise, you will
Yes,
never.
is that so this screen is fixed at a value. Let's say 1 unit in this space.
Yeah.
This fx, fy, fz gives this image plane. So its z coordinate is fz and its expanse in x and y is fx and fy. So it's a plane in the space.
Okay.
Equation of a plane in the space. And that projection. So if we take the cone and if we directly take a sphere and project it, that would give a different ellipse than the, because if we are looking in this way, the plane might be tilted, so the ellipse might.
So I'm asking, are you allowed to tilt the plane to get the
No,
desired image?
that is fixed.
So the camera is fixed and so you will not work with balls then, you have to work with ellipsoids. You see what I'm asking? Because if the plane is fixed and the camera is
Yes.
fixed, then how are you going to get a ellipsoid unless you're allowing the thing to not be a ball?
Because the original tube is assumed to be a sphere trace. That's union of spheres. And in the capsule envelope, we will show like this is a quick estimate, but not very good accurate. This gives a better result, but it takes more
I
computation.
think you can, I guess what you're saying is if you have a light source, if you're just directly projecting a sphere, you will get a circle.
Yeah.
And you want it to be somewhere up. Maybe so
Yes.
but you can assume the screen is large enough. And
It's done.
the spectrum might be huge enough. and you're
Assuming the
exactly
sphere
where-
is totally inside the frustum.
Okay.
Because in this computation, the frustum is not there. It can be out, even for a query point outside the image state, we can compute, but that would be handled differently. So we'll get this ellipse renderer, and for the capsule renderer, we assume these two lines. So we already found the ellipse from the two spheres. Now we want the points P1, P2, P3, P4 to get the quadrilateral. So if these lines are parallel, then they won't meet, and there would be other way to compute those points. But assuming that those lines do meet at some point, then we call this as the vanishing point, x0, y0. Now, let's say this line joining P1 and P2 is given by capital L. And if we take this line, so if we increase the z value of the line and divide it by the fz, which is the z coordinate of the plane, because this line will always get projected on this plane. So the projection of this line on the plane might be a finite line segment, depending not the segment, but after normalization. So when viewed from the camera, if we look at this tube going along this line, it would appear to converge at a point. So that is the vanishing point, which is given by x0 and y0. And let's say we found an ellipse using the previous method. This is the ellipse, and we want to find P1 and P2. So let y is equal to mx plus c denote line passing through x0, y0. So substituting, we get this line passing through x0, y0. And if we equate it with the ellipse, substitute y in this ellipse equation, we would get this. And since we know that it is tangent at this point, then there should be double roots here. So this square minus 4 times this into this has to be 0 for the quadratic. So using that condition, we would get a 4th degree polynomial in M, but the 4th and the 3rd degree coefficient turn out to be 0. So we get this quadratic. So making discriminant that p square minus 4 is equal to 0 in a quadratic. For this quadratic, we get an equation in M, whose 4th and 3rd order is 0. So we get a quadratic with these three coefficients. And here again, all these terms are differentiable with respect to the original points. Although this is differentiable, there are sometimes numerical issue if these two spheres are almost on the same breadth, where these denominator might become close to 0. Because for computing the value of M, we would do b square minus 4ac by 2a, the root. And if it is
means that we don't have this vanishing point.
so it numerically it gives very large values. So it's numerically unstable, so it has to be handled. So for those cases, we have to give a epsilon region that if it is very small, then do not compute using these methods. So that has to be answered. But apart from those numerical issues, this is differentiable and works. So these are the rendering result for a circle. So we have a circle whose depth is changing. This is how the circle with circular tube, which is going far away here. This is how the actual rendering should look. So in the ellipse renderer, as we increase the number of points, we get better results. But if we use finite number of samples, we don't get very good result. But in the case of capsule, even for less number of points, we get it's at least continuous, it doesn't break in between. And increasing the softness factor, which was in the occupancy equation, how much soft or hard the rendering should be. So if you want a very crisp image, you have a high hardness factor, which gives a very crisp image, and for a soft rendering, we get this blurring. So the importance of this is, since this tau is in the exponent, setting high value of tau would give you a good looking image, but it would cause numerical instability while training. So we might want somewhere here where it looks good and there would be a safe region to. And so this is the result with applying length loss. So if we have a high penalty for length, so if we do not allow length to increase, it finally learns a very small, tiny line segment. But if we give it freedom to change in length, it learns to approximately target shape. And similarly for bending, if we penalize on the bending, it cannot become anything other than a circle. And giving it freedom, it can bend to form rectangle looking shapes. Similarly, we have for the occupancy loss, where it works for depending on how much weight we use. And the Mobius law was for self-intersection of tube. So the curve in itself is guaranteed to have no self-intersection because we were using homeomorphism and we had a template circle. So any embedding of that would not have self-intersection. That is guaranteed by design. But when we are taking a R radius sphere, the tube can have some self-intersection. So there is guarantee of that knot is self-intersection free, but the tube need not be. So this we penalize for the tube. And so for high weight values, we see that it is not able to, it does not self-intersect. And here we purposely give it target shapes where it has to intersect. So this is the Viviani curves projection. It shows infinity and zero. And so these are some of the results. These are the target shapes we have given, and this is what the knot has. This is what the renderer sees after the knot is found. Again, this is the target, and this is the results. And so here I'll show a video where during optimization how the knot is deforming. So we give an image of Iron Man and a rabbit. And this is the initialization of the knot, which gives an initial rendering, and it tries to optimize it.
And what's the thing on the bottom?
This red is the light source. That red is the light source from the lightest plasma. And so we have we also created a real world demonstration. Given this target image, this is what our network learned. And so this is a shadow, and when you look at it from the location, this tube would also appear like a smiley. And we took the knot shape and created a 3D print of it. And this is we shown light and this is smiley. And this is how it looks. So I carry this structure with me. I can show up the top. And so then for if we leave the concept of physical realizability, and if we allow self-intersection, so we wanted to see if it can learn complicated structures. So we can allow self-intersection in the tube, then it can learn aeroplanes and also chairs. So here there would be some self-intersection in the tube, but it can learn complex shapes.
There is a small. Why you were also like, is there a necessity to work with one single thing or different?
One single knot.
Yes.
No, so here we have a single knot, single viewer case. So even the view image constraint need not be single. You could say that.
So my point is that if the shadow contains some isolated point, one black spot and then again, like a circle.
Okay.
So in that case, we can work also with. We have to work with at least this
Yes.
slots, right?
Yeah, so in that, if you force it to learn with one knot, what would happen is it would learn this shape, try to go very far away so that the projection is very thin.
Yes.
And then try to learn them. But I've tried for the here I've not included for the multi-knot. I've done some experiment on multiple knot. The computation increases a lot for every knot because for every knot you have to sample.
But it might happen that if you use more knots, the cost length of the might
Reduce. Yeah, it would. So here we just wanted to check a given circle, how much complicated shapes can one loop make. So we have done something with multiple knots.
Hi, sorry, that's a stupid question. So here you are asking for border exclusivity where you remove the crossing constraint. But a very stupid question that so if we have a crossing constraint, then why is this so hard to do?
Because let's say it has occupancy, let's say we have this fire and I confine it to be within a fixed region. If you want to make some thin structures, let's say if you want to make this thin structure, right, the wire would have, if it's a thick tube, it might have to go very far away from the camera so that it appears thin. But it doesn't have the liberty to go away from the occupancy region.
What about the chair? I think that did not have any sense.
Yeah, here we removed the occupancy constraints also.
Oh, I see.
I mean, the self intersection, we removed all constraints. Just it should create the image. So all constraints removed. And this is the result for. So this is the shadow, and this is how it looks from the front. And this is.
So can your algorithm also prove this? That hey, this is not possible to do.
So here it's not binary, it's more of a continuous loss based. So it can't say this is true or the solution does not exist. It would try to do its best and find a minimum. It would, given a initial location, it would try to go in some better place.
So yeah, but I guess maybe it's non-convex. Because obviously those certificate you can get that.
Because this algorithm doesn't know whether there doesn't exist a solution. It might just get stuck somewhere. So and so we can have multiple viewer constraints where if there should be a casting, it should cast shadow of this shape in this one, and under this multiple constraints we found this shape. And this the image I showed before for different constraint values. And finally, we gave a sequence of images. We took a video and gave sequence of images, and the objective is the knot has to deform in time, in space and as well as in time, so that if we look at the animation of the knot, the shadow casted would give a person dancing. So it learned, these were the learned renderings, and this is the skeleton of the knot. So these are all the at different times, time 1, time 2, and final time. These are the embeddings. And if we look at the video, this is how the video looks. The knot is deforming with time.
So in this case, is there a loss in terms of the time derivative? Is not also?
Yes, so we also the two these should be similar. So we took the phi value, the embedding, and the norm between that should be minimized. The consecutive frame should be similar. So a related idea is that of not untangling. Since we have an embedding for knot, let's say we are given a messy knot in a messy tangled way, and we want to simplify it. So untangling here would mean that we cannot change its knot type.
But in this case, I thought you're only going to get unknots, right? Because you're taking the image of a
Just I'm going to the next.
did something else.
This is unrelated, like next part on this part. So if we don't take the rendering part, only the embedding part. So given this tangled knot, yeah. So in the previous one, I've just worked with the single and knot, but we could have it works for any other template shape, and even for, let's say, if you take some tree graphs kind of shapes, wire sculpture, complicated tree graphs, you could even run for this, but I've not experimented. So given a tangled shape, you might want to learn a simple untangled form of the knot. And if we use the same idea here. So the objective is, given the tangled knot and the homeomorphism, you find the deformation of that. And if we try to minimize the energy, which says how much tangled it is, then in order to minimize this energy, it would learn a deformation. And that in turn would be the untangled knot. So the advantage here is it doesn't, it preserves the topology of the knot. So it makes sure that the knot type is not changed. So for example, we could use repulsion based losses. So here we use a mixture of these two laws with weights. So we can choose some energy, and we have to minimize that energy for finitely sampled points under the constraint that the length must remain fixed. Otherwise, the repulsion would keep growing. The knot would keep becoming bigger. So we have the length constraint, and we made a small test bed of 6 shapes. So this is the simplest, and it keeps becoming progressively difficult. And we show the results for those 6.
So if you have something that is actually knotted and try to do this, what happens?
Something which is
Actually knotted. So the minimum.
Oh, it's not an unknot.
Yeah.
Oh, so it would try to find for that. I've not done yet. So this is a very small experiment I've done.
We've done it for only things that are not knotted, and
I've run, but there is a knot data set, untangling data set. Those are all shapes are very complex. Those are very tangled. So it didn't work for that. So I started with a simple test bed. So we have to do for that. So for this simple shape, that is able to untangle it after a while. So here it's untangling the shape. So here it is untangling into a. Here it's. So here it gets stuck in this. So after for very complex, it's difficult after a particular point to untangle. Okay. So I'll move on to the next problem. So so the Escherization problem is given a first I'll talk about Escher styling, where Escher was trying to create shapes of tiles which resemble animals, and those are tileable. So this is an animal looking shape, and that can tile the entire plane. Similarly, here is a fish, and this is a reptile shape and fish kind of shape. So all these are shapes are perfectly tileable. So similarly here we can see here it is a one translation unit, and that keeps repeating to the entire plane. So the Escherization problem is given an input shape, let's say like a rabbit, we might want to find a shape similar to the rabbit, which is tileable, which can tile the entire space. So the assumption is that this shape is of is a closed disk with a boundary. And the shape we want to find should also have closed disk topology and countable copies type. And let's say we have a distance metric between shapes, which says how similar two shapes are. So we want to minimize that distance. So I'll go over it quickly here. This part introduction now. So the isohedral tiling means if two tilings are linked by a symmetry, then that symmetry is also a symmetry of the entire tiling. So here, if we look at two shape, whatever transformation takes this shape to this type, the entire space, if you apply that transformation, gives the same tiling. So that is isohedral tiling. Here, this is not isohedral because if we flip about this axis, A goes to B, but the entire tiling doesn't go to C. Then isohedral tiling, that constraint needs to be satisfied. So there have been previous works on actualization where the tile shape is assumed to be a piecewise polygon, piecewise linear polygon, and they define constraints on the adjacency. So how the tiles are adjacent. So this gives rise to many isohedral classes. So one of the work, they have parameterized all the 93 isohedral classes. And in the isohedral classes, we might have such kind of constraint that these two edge are the same. K2 is same as K2, and this is K3. So this shape gets attached over here, so it shows the identification. So I'll explain our approach. In our approach, we have a differentiable representation of the shape, and it is not a polygon, so it can have arbitrary curves. So the shape is not polygonal. It can have it is a deformation of some template, so it can have complicated edges. So given a target shape, and let's say we have a hexagon here of our template. So we would have constraint diffeomorphism here, where these are the constraints. So let's say if we want to do this using diffeomorphism, where we want to smoothly deform it. If I deform this edge slightly here, then this edge should also get perturbed in the same way. If I bend K2 here, the effect would also show here. So we have this constraint where if I make change in one place, in another place, the change should reflect. So we have those constraints here. So under those, so I'll explain later how we make this constraint diffeomorphism. But let's say we have made that. Then if we forward pass this hexagon, it would become some deformed shape. And we want this deformed shapes to be similar to the rabbit. So these are points where it's inside rabbit and also inside shape. This is outside the shape and also outside the rabbit shape. And these are points where it's inside the template but outside the rabbit, and inside the rabbit but outside. So we want to penalize this red type of points. That's the approach we'll take. And in practice, in application, while applying this, we do it in the inverse direction. So we take the rabbit and deform we take points here. We sample points from this space, and we know already whether it's inside the rabbit or outside the rabbit, and we deform them. And in the deformed space, we see whether it's inside the blue hexagon or not. Because the hexagon is a simple shape, so we have the sign distance function, algebraic form of that. So you can easily compute the occupancy as in the previous method, a soft value between 0 and 1. And we can apply classification laws. So from here, we can sample lots of points. Some would be having label 1, some would be having label 0. We do a diffeomorphism, and after mapping, we would compute the distances here. And if there is a mismatch, then we penalize that. And it would try to learn a deformation of the hexagon so that it becomes a rabbit. Now I'll explain the diffeomorphism. So this is the idea I just explained, the occupancy and the classification loss. And so the idea of diffeomorphism uses initial value problem. Where let's say we have an initial value problem and this is Lipschitz continuous, then this would have a unique solution. then we can use a unique solution to integrate from 0 to some initial time to final time, so that one point flows to another point. Let's say we have an initial value problem, and we define the diffeomorphism of a point Q. We treat Q to be at time 0. Then at time 1, we get the value by integrating it to this flow from T0 to T1. And that's the diffeomorphism. And I'll go over this quickly. So there was a new paper called Neural ODE, which made the ODE solvers differentiable. So you have a ODE solver of your choice. You considers it as a black box and makes it differentiable. So without going, it doesn't matter which ODE solver it is. So then it becomes possible to define, to backpropagate to find these thetas. So here, for a different value of theta, we get a different diffeomorphism, and it can backpropagate to the entire process. So here, given all these classes, isohedral classes, these are the constraints. We can see that there is periodic constraint in all of these cases. In many cases, there is transflexion, that is glided reflection. So reflect and translate. And in several, there are rotation symmetries. So here we have 6-fold and 3-fold rotation, and here we have 4-fold rotation. So we have these 3 symmetries which arise in this problem. And we want translation invariance, that is, if the flow at this point is in this direction, at any translated copy, that should be the same. In transflexion, we want, if it vector is in this direction, after reflection, the flow vector should also reflect. And in rotation, there should, if we take at k-fold rotations, the flow vector should be rotated copies. So here given, so we use Fourier basis here for the periodicity. So given a basis, this lattice basis B1 and B2, this Fourier in 2D is it's periodic. It's defined for the unit square here, and using a change of basis, we can define it for any parallelogram shape. And for rotation, we use this method to symmetrize. So let's say we have k-fold rotation. So capital R is all the rotation operations, all the rotation group. So let's say there are 6 rotation elements here. So given a query point Q, this is the origin and this is the center of rotation. We rotate it around this center, compute the flow at this, and then inverse rotate the flow. And we do this summation for all rotations in this. So this ensures if we take this capital F to be the final flow, then these 6 points would have the rotational equivalence property satisfied. So this ensures that.
It is proper final.
Yeah, okay. So I'll quickly go to the results. So we implement for the all the classes, we design the symmetries for them. And show some result. So here is the shape, red outline. The black is what it's trying to learn, and here is the tiling along with. It's has a guaranteed tiling here. The tiling also is perfect, and it tries to learn a rapid shape.
So this particular rabbit shape has a tiling.
Yes, these are the tiling.
No, it's the exact red thing also has a tiling.
No. That's an arbitrary image from the internet. And there's the actual flow which we know, and this is the flow during the optimization, and we can see that it has those guaranteed symmetric properties. So the resolution is low. So it learns the flow over time. And this is the flow with the vector lengths, the flow field vectors, that was magnitude. And this is for all the classes. So for different classes, we get different dimensions. These are what are different the tiling for different classes. And I'll finish with one last slide. So you can use the same idea to define flows on identification spaces, where identification spaces are similarly defined identification constraints. So we define flows on torus, sphere, and triangle and projective plane, and we use it for density estimation. So I'll show some results. So here we have 6 Gaussians. Go to the next slide. For all the 4 cases, the top one is probability and the bottom one is log probability. So it tries to learn 6 Gaussian density. So a single template Gaussian distribution is deformed to foundation. And another result for checkerboard, that's the last. So here it tries to learn checkerboard pattern on all those 4 identification spaces.
Rendering all of the things.
So the not one in Blender in 3D software, and these were during problem. So here it's on based on the color map, it looks so for all the probability values are computed, we create the image using and some of the illustrations.
All your slides.
So then Google Slides. So the rendering is outside and yeah, the